Hey everybody, and welcome to Quesadilla Math with me, Mr. Padilla. Today we're going to be talking about how to graph absolute value equations using vertex form of an absolute value function. So let's get started. Let's start off by discussing some of the characteristics of a graph of an absolute value function. Graphically, absolute value functions are V-shaped. Here we're looking at the parent function of an absolute value function, y is equal to the absolute value of x. This is the most basic form of an absolute value graph. And here you can see a couple of the important characteristics of the graph of an absolute value function. It has an axis of symmetry, and this is a vertical line that separates the two symmetric halves of our absolute value function. In this case, they are two lines, and that axis of symmetry passes through what we call the vertex, which is where these two lines meet. In our case, the parent function y is equal to the absolute value of x. Our vertex is at 0, 0, otherwise known as the origin, and the axis of symmetry is the y-axis, the line x equals 1. Now, as I mentioned before, you can think of the graph of an absolute value function as two lines. One line with a positive slope. As you can see, on the right side of the vertex, we have a positive slope. And on the left side of the vertex, we have a negative slope. This is true for y is equal to the absolute value of x, although sometimes the right side will be negative, the left side will have a positive slope. It depends on the specific equation for that absolute value. Now we can investigate a little bit further into why we have a V shape for the graph of an absolute value function. As you may be familiar with an absolute value in and of itself, what it does is it takes the distance of any value placed inside the absolute value to 0. In other words, it makes every value that you place inside an absolute value a positive one. Let's see how this works. We can start off with the absolute value of 0. If we let x equal 0, we'll take the absolute value of 0, and of course the absolute value of 0 is equal to 0. If we take x equals 1, we'll plug in the absolute value of 1, which of course is 1. So we have the points 0, 0, and 1, 1. Now if we take x equals to negative 1, the absolute value of negative 1 is equal to positive 1. So we get the coordinate negative 1, 1. If we plug in x equals 2, we get the absolute value of 2, which is equal to 2 as well. So we get the point 2, 2. Same thing happens when we plug in negative 2 for x. The absolute value of negative 2 is also equal to positive 2. So we get the coordinate point negative 2, 2. Now, as you can see, the slope of our right side is going to be 1 over 1. If you think of slope as being rise over run, from one point to the next, we have to go right up 1, rise up 1, and to the right 1. Rise up 1 to the right 1. For the left side, it's the complete opposite. We go up 1 to the left 1, up 1, left 1. So this has a negative 1 slope. This has a positive 1 slope. So now let's learn about how to graph an absolute value equation other than our parent graph y is equal to the absolute value of x. To do that, we're going to be using what's called the vertex form of an absolute value equation, which is y is equal to a times the absolute value of x minus h plus k, where a, h, and k will always be three values that will tell you some important characteristics about your particular equation and the way it will be graphed. Now, the point hk that you can find in the equation here, the point hk is called the vertex. You can think of the value of h as being a horizontal shift of the parent function, and k as being a vertical shift of the value of the graph of the parent function. The value of a will be what represents your vertical stretch and compression, where a, the value itself, is always the slope of the right side, and negative a, the opposite of that, will be the slope of the left-hand side of your graph. So to help understand how this equation works, we will start off with changing the values of the vertex and seeing how that affects our graph. For our first example, we will be graphing the equation y equals to the absolute value of x minus 3. Now, once again, we're going to be using our vertex form y equals to a times the absolute value of x minus h plus k to help us graph this. Let's start with the vertex. So comparing our equation to our vertex form, we can see that there's no number in here with inside the absolute value with the x. So that tells us that h is equal to 0. And outside the absolute value, we have the absolute value minus 3. So that tells us that k is equal to negative 3. So our vertex is going to be the coordinate 0 and negative 3 because it's always h, then k. So here we graph 0, negative 3. We can get the rest of our absolute value equation by using the value of a. In this case, there's no number that appears to be multiplying our absolute value, so that means that a must be equal to 1. So the value of a tells us the slope of the right-hand side starting from our vertex. In our case, the right side slope is 1, or you can think of it as 1 over 1. Don't forget that slope is equal to rise over run. So that means we would go from the vertex, up 1 to the right 1, then from there, up 1, right 1, and we would continue that pattern. On the left-hand side, we would have a slope of negative 1, which means we would, starting from the vertex once again, go up 1 to the left 1, up 1, left 1, up 1, left 1, and so forth. Now, we can draw a line through our points for both of these two lines, and we have graphed our absolute value equation. Now in example 2, we are graphing the equation y equals to the absolute value of quantity x minus 2. Again, here we will start off by identifying our vertex. In this case, we do have something being added or subtracted to our x value inside the absolute value. And comparing our equation here, we see that h is actually equal to positive 2. You might be thinking to yourself, it says x minus 2 inside the absolute value, so how can h be positive 2? Well, because our form of our vertex form has x minus h, the h value, because of that minus, is always going to be the opposite sign of what you actually see in your equation. So if you see x minus 2, the value of h will be positive 2. If you see instead x plus 2, that's when you'll have a negative value for h. So it's always the opposite sign of the value that you see inside the absolute value. In this case, k is equal to 0 because there's nothing being added outside the absolute value. So our vertex is going to be at the coordinate point 2, 0. Once again, the value of a in our equation is equal to 1. So that means the right side slope of our equation is also going to be 1. So I go up 1, right 1, up 1, right 1, up 1, right 1, starting with the vertex. And the left side slope is negative 1, so we'll go starting with the vertex, up 1, left 1, up 1, left 1, and so forth. And finally, we can draw our lines through our points to graph the absolute value function. In example 3, we will graph the equation y equals to the absolute value of quantity x plus 1, then minus 3. Once again, we'll start with the vertex. In this equation, we have h equals to negative 1. Once again, the opposite of what you see here. Here you see x plus 1, but the value of h is negative 1. The value of k is going to be negative 3 here on the outside of the absolute value. Notice how the value of k does not change value. So we get our vertex negative 1, negative 3. Once again, we have the value of a equal to positive 1. So that means the right side slope of our equation will be positive 1. So we go up 1 to the right 1, up 1, right 1, and so on. And for our left side, we'll go up 1, left 1, since the slope is negative 1. Then finally, we can connect our coordinates and finish drawing our graph. So now we'll investigate how a different value for a will affect the shape of our graphs. In example 4, we have y equals the absolute value of quantity x minus 2, then plus 1. And looking at our equation once again, we see that h is equal to 2 and k is equal to 1. So our vertex will be at the coordinate 2, 1. And our right hand slope once again is a equals 1. And the left side will be the slope -1. So now let's investigate how the value of a will affect the shape of our graphs. In example 5, we'll be looking at the graphs of 4 different absolute value functions to see if we can determine the value of a from each graph. In our first graph, we have y is equal to a times the absolute value of x. And to figure out the value of a, all we have to do is figure out the slope of the right-hand side. In our case, if we go from one point to the next, we can see that the slope is up 2 to the right 1, up 2 to the right 1, which means our slope is equal to 2. So in this case, a equals to 2, just the slope of the right-hand side. In our second graph, we see that the rise of a run is 1 over 4, 1 up, 4 to the right, which means our right-hand side of this function has a slope of 1 over 4, which means that the value of b here, which is our a value, is also 1/4. In our third graph, this time our right-hand side of our equation of our graph has a negative slope. It goes down 1 and to the right 2, down 1 to the right 2. So our value for c here would be -1/2. Again, this just represents our a value. And in our fourth graph, we see once again we have a negative slope. From one point to the next, our graph goes 4 down and 1 to the right, 4 down, 1 to the right. So that means that the value of d in this case is equal to -4. So the value of a, no matter which letter we use to describe it, will always describe the slope of the right-hand side of your graph starting from the vertex. In example number 6, we will be graphing y equals to 2 times the absolute value of x. Starting with the vertex, we can see that we have no values adding to our x or outside adding to the absolute value. So that means both h and k are equal to 0, meaning our vertex is at the origin 0, 0. The value of a in our equation this time is equal to 2. So that means the slope of the right-hand side of our graph, starting with the vertex, is 2 over 1, meaning we go up 2 to the right 1, up 2, right 1. The left side slope is up 2 to the left 1, up 2 to the left 1, since the slope is -2. And drawing lines through our coordinates will give us our nice thinner V shape for this graph. In example number 7, we will graph y equals to -1/2 times the absolute value of x. Once more, our vertex will be at the origin. Since the values for h and k do not appear in our equation, they are both equal to 0. This time the value of a is equal to -1/2, which means the slope of the right-hand side of our graph is going to be also -1/2, which means instead of going up this time, we're going to be going down 1 to the right 2, down 1 to the right 2. The slope of our left-hand side is going to be down 1 to the left 2, down 1 to the left 2. And you can see now that it is a positive slope. So that is how we graph that equation. For example number 8, we will graph y equals to 3 times the absolute value of x plus 4, then plus 2. Starting with the vertex, we can see that the value of h is equal to -4, the opposite of x plus 4 here, and k is equal to +2, so our vertex will be at -4, 2. The value of a in our equation this time is equal to 3, so that means our right side slope is +3, so starting from the vertex, up 3 to the right 1, our left side of the slope is going to be up 3 to the left 1. Connecting our points allows us to complete our graph of this equation. In our final example, we'll be graphing the equation y equals to -4 times the absolute value of x minus 3 plus 2. This time, our value for h is +3 since we have x minus 3 inside the absolute value, and k is equal to 2, so our vertex is going to be at 3 and 2. The value of a in our equation is equal to -4, so that means the right-hand side of our graph is going to have a slope of -4, so that means down 1, 2, 3, 4, to the right 1. And our left-hand slope is going to be down 4, to the left 1. So then our absolute value graph looks like this. So I hope that this helped you learn how to graph absolute value functions. It really is just a step above graphing a linear function. So I hope that this made a difference for you. If you guys liked this video, please leave a like and subscribe to this channel for future videos to help you with your math. And as always, I'll math you later.